G'day, this is Richard Walding here again. I want to have a look at the next topic in particle interactions. Now this one's called Feynman Diagrams. I've put the reference there for this textbook here. So for my textbook, the New Century textbook, chapter 14.2, and there's the page numbers that I'm going to be dealing with. Now, Feynman diagrams, just quite simply, are just pictorial or graphical representations of particle interactions. So if you've got two particles that interact, you can depict them with Feynman diagrams. And in this case, let's imagine I'm talking about, say, two electrons, or you could be talking about an up quark doing something, and so on. So it's just a graphical representation of the interactions. You've got to be careful not to read too much into what the diagrams look like. They're being presented in a way that we're just looking at the simple version of the Feynman diagrams. To physicists, there's a lot more in the diagrams than we would you'd know from just looking at them. Okay, Richard Feynman, they're named after Richard Feynman, a brilliant US scientist. There's plenty of books been written by him. Here's one here. And some of the stuff he did was just so fantastic that it solved a lot of the problems in physics at the time. When I talk about him to my students, I think the thing that they're most impressed by is he can remember pi up to a couple of thousand decimal places. Let's have a look at his diagrams. There's a few conventions, and then we'll go about look at the particle interactions. Now these are the conventions. The first convention is that you put time along the bottom and space up the side. Now some places have time up the side and space along the bottom. Now for the syllabus, it makes it clear that that's how they're going to present the work in any external exam, and that's how I've done it in the textbook, and most people do. I think you'll find some diagrams in Wikipedia that are reversed. Now it's not hard to change the axes around. You just flip the diagrams. But it's space and time. Now you've got to be careful with Feynman diagrams. There's no scaling of the time or space axis, so there's no numbers on it. And the other thing you've got to be careful about is that we're not talking about space like the displacement of a particle that's moving with time. Now you're familiar back in the linear motion days where you could represent displacement versus time and you'd get all sorts of graphs. Now that's not what this is about, so don't think that's representing displacement. It's just how these particles move in space. Okay, so that's the first convention. The second convention is that you represent particles by a line like that. So for instance, particles such as quarks and leptons can be represented by a straight line like that, and you put the symbol on it. So that could represent an electron. Now it could be at an angle like that, it doesn't matter. If you're trying to show the particles coming together, you might put them at an angle, or you could put them up like that, it doesn't matter. Just so long as you've got the arrow going in the same direction as time for a normal sort of a particle. Okay, now a quark would look the same. You might have a quark and you might say up, and that would be representing an up quark moving through time. And in terms of space, it's, it could be stationary, but it could be moving, could be coming together or something like that. So that's the second convention. The third convention is for antiparticles. Now with antiparticles, you represent them as going backwards in time. Now this is a bit tricky. A lot of people say, but they can't go backwards in time. This is a graphical representation of the processes, and the simplest way to represent a antiparticle is to have the arrow going backwards in time, and then everything works out. The maths behind the diagrams, all the calculations of all the the possibilities work out if you have it going like that. So an anti-electron, in other words a positron, could be like that, or it could be like that, or like that. It doesn't matter. Whoops, E plus. Okay, so, and if you had an anti up, for instance, it could be like that. Okay, so the main particles we deal with will be electrons, quarks, and some of the neutrinos, the electron, like say the electron neutrino or something like that. Now a neutrino, of course, would just be like that. That's an electron neutrino. It's not an antiparticle. An electron antineutrino would be like this, okay, with the bar above it. And the same if it was a muon or a tau particle. But as far as the syllabus goes, we're only talking mainly about electron interactions, electrons and positrons, and neutrons and protons. So a neutron, for instance, might be like that. Okay, so you're talking not about quarks and leptons, but neutron, which is a composite of quarks, and a proton would be the same. You might put a plus in there. An anti-neutron, of course, would be like that, just as long as the arrow is going backwards. So that's the representation, the first three conventions. The fourth convention, so one, I'll label them, 1, 2, 3, that's the antiparticles go backwards in time. 4 is the gauge bosons. Now, you've got to be a little bit careful here. We're only talking about gauge bosons with these diagrams. Now, I didn't make it clear in an earlier talk that elementary particles, I said they're bosons, and there's a group within them called gauge bosons, and I tried to explain that. Excuse me. But here in Feynman diagrams, we're only talking about gauge bosons, not what we could call composite particles that are also bosons. For instance, now I don't want to confuse you here, but a particle like, say, a meson, which is a quark-antiquark particle, now that's said to be bosonic. In other words, it has the same properties as the gauge boson in some ways in terms of its spin. Now, we're not doing spin in senior physics, so you can almost forget that I said that, but we're not looking at composite particles that are bosonic or bosons. We're only looking at gauge bosons, and you've seen those before. I'll write them down so there's no problem. We're looking at the gluon, or which would be G. We're looking at the W plus and W minus bosons, and the Z boson, and lastly the photon. So they're the 5 bosons, which in the syllabus we call them 4 bosons. In the text I've called them 4 bosons, 4 gauge bosons. 1, 2, 3, so you get the W. I should do it like this. Okay, so 1, 2, 3, 4, 5 bosons, but we can lump those two together as just the W boson, and there's 2 versions of it. They're charged, so plus charge, minus charge. So now we represent a gauge boson with a curly line like that. Okay, and you might put on it, say you were talking about the W minus boson, it'd be like that. Now, and it could also be going at an angle, it doesn't matter. Now, we're not going to put an arrow on these. You could, if you like. Now, some books do. They tend to put a straight line and call it W minus, and they indicate that the minus is the antiparticle of the plus. Okay, so a W minus you could actually have as an antiparticle, and this thing as a particle. But in the senior physics syllabus, we're not talking about whether they're antiparticle. Oh, sorry, this would be W minus would go back. W plus would be like that because it's the particle. So it goes forward in time. The antiparticle goes back. The syllabus doesn't talk about the difference between W plus and W minuses in terms of whether they're particles or antiparticles. And I haven't mentioned that because the syllabus doesn't do it. It just says you indicate a gauge boson with a squiggly line. Now, the only ones you'll be dealing with will be the W plus W minus, the Z, and the photon. The gluons actually won't be used in the diagrams that we're doing for senior physics. They actually have a curly line, but we're not doing gluons, okay, for Feynman diagrams. So we're going to leave it at that. The main point I was making was gauge bosons are elementary particles. They're single with no substructure, okay, whereas you can have some other bosons, such as the meson, which are made up of quark and antiquark, which are still called bosons, but they're not gauge bosons. Okay, I know it's complicated, but that's the main point. So they're the 4 points about conventions. Now, the second thing to look at is how do you represent interactions? Okay, so they're the conventions for the particles themselves, but how do you represent interactions? Now, there's a couple of things you can do here. Let's say we're representing an electron travelling in time that way. Now, it could be a bit of an angle, it doesn't matter. We use a dot on one end. Now, that dot's called the vertex. Now, it's just where things happen, where the interaction happens. So that's an electron coming in, so that's an inbound electron. An outbound electron would be like that. Okay, so it's still arrow of time, or the arrow going that way to indicate it's a particle, not an antiparticle. So this is the incoming, that's the outgoing. Now you could also do this. An incoming positron would be E+, but remember for antiparticles the arrow points in the opposite direction of time, so backwards in time if you like. The antiparticle going out would be that. Okay. Now bosons or gauge bosons would be represented like that, coming in, and a gauge boson going out would be like that. Now you might have W minus or something, it doesn't really matter, whatever you've got. It could be or light, you know, a photon of light, or excuse me. So that's how you represented that. Now internal lines, so they're the incoming, outgoing, but when they interact you might indicate them like this. You might say the interaction is via a, let's say, a W minus particle. So you've got something coming in, then they interact, those electrons or whatever interact, they interact via this gauge boson, which is the force particle, and then there's something going out as well. So that's for internal lines. So internally you'd have a vertex at either end where the interaction takes place. Okay, so that's the lines. Now the next point in that is you'll always have 3 lines at a vertex. Now VERTEX. Now the 3 lines, 2 of them are going to be either, I hate using the word fermions here because that's not a syllabus term, but let's have a look. Say for instance you had something like this. So there's 2 electrons coming together, they're approaching each other and something happens to them. Let's imagine they do that and they turn into a photon of light. Now this would be something like, here's my 2 electrons, they're coming together and something happens at the vertex and they turn into, you know, a flash of light if you like, a virtual or a photon. Okay, so that's how you'd represent it. What you'll notice is there's always 2 either electrons or quarks, or, well, that's about it. Or sometimes you can have a quark composites. You could have a proton coming in and doing all sorts of things. Okay, but they're basically 2 matter particles and a gauge boson. So you always get 3 lines at a vertex, 2 matter particles, either a quark or a lepton, or a composite quark such as a neutron or proton, and the third particle is a gauge boson, so it could be W plus, W minus, Z, or the photon. Now it's not a squiggly line, it's not a gluon, because the syllabus is not asking you to look at gluons. Okay, so that's that. Now before we get on to what the syllabus could ask you, the syllabus, the term in the syllabus for this is to explain, using Feynman diagrams, what turns out to be 5 different types of interactions. The last 2 would be this way. The last 2 are 2 versions of the same interaction. So the 5 are electron and electron, electron and positron, another type of electron and positron, decay of a neutron, and another version of the decay of the neutron. So there's 5 different diagrams you have to learn. There's no simple way around this, you've just got to learn them. Now the question in the external exam could say draw one of those 5, and it'll give its name and you just have to draw it, and might say label it, it might say explain. Now in the syllabus the cognitive verb is to explain Feynman diagrams of those 5 types. Now explain is not just drawing it and labelling it, you have to make it clear. So a part of explaining, the verb explain, is to make clear by describing extra properties of it, or extra particles. You can't just leave it as a simple diagram or a couple of words. You've got to describe extra features of the diagram or the process to make it clear. So make clear is the key part of this. So what you've got to do is to make clear some of these Feynman diagrams. And I'll go through them in detail. Now the other thing they could ask you, probably as a multi-choice question, would be, here's a diagram, they'll give you one of the 5 and they'll say which one of these four options is represented by the diagram. And it could say an electron scattering, it could be electron positron annihilation, or a neutron decay, something like that. Or it could even be not one of the 5, it might say quarks combining to form a meson, or whatever, just something to trap you. Okay, so we'll go through all of that. Let's have a look at a couple of simple ones now and see if you can work out what these would represent. Now these are only half the Feynman, they're still Feynman diagrams, but they're not the full ones that you'll have to do in the syllabus. Can you imagine this? Now what's happening here? Okay, now that could be, and I'll label that as a photon. The question is, what could be happening there? Now what you've got is, and you'd have to explain this if that came up as a question. It's only a part of a diagram, but you want to get practice at just explaining these using the right words. Now you can see what's happening here. You've got, let's imagine, here's my electron and here's the photon. So what's happening is they're coming together. Now I know this is, I said before, they're not representing displacement or anything like that, but this is a good way of just visualizing what's going on. So here's the photon and here's the electron. So they're coming in together, they hit there, the photon is absorbed by the electron and the electron keeps going. Now you've seen this over and over again. You've seen these diagrams. Now if you think of the spectrum of hydrogen, you might have n equals 1, n equals 2, 3, 4, and infinity, or something like that. And you take an electron from there and send it up to there. Okay, so there's a transition. Now this goes back to your work with hydrogen spectrum in the earlier quantum physics part. Okay, so that's an electron in energy level 2. It absorbs a photon and hops up to energy level 3. It's still an electron, but the electron has absorbed that photon. Okay, so it's got a lot more energy. The electron's got more energy. So that can be represented by this process here. Now it's not that hard. Look, here's a book I bought for my grandson, Quantum Physics for Babies, but I read it to my grade 12 class and I used this part here. They loved it. So here's a electron in energy level 2, and you can see the light coming in, and there's the electron has jumped up to the next level. Okay, so that's all that's happening there. Now, as well, you could have something like this. You could have an electron coming in. Now, it doesn't matter if it's in an angle or not, and you could have something like this. That's a photon. And you'd say, describe that. In your words, you'd say, an electron emits a photon and then continues on its merry way, effectively, but it continues on with a lower amount of energy. Now that'd be something like this. The electron is at level 3, so it's a higher energy electron, and then it drops, it transitions, and it actually gives off a photon of light, which is your spectrum, a part of your spectrum. That's one of the first lines in the hydrogen spectrum. You probably, well, you should remember there are, there's 4 lines in the hydrogen spectrum. There's from 3 to 2 is one of them, 4 to 2, 5 to 2, and 6 to 2 are the 4 visible lines in the hydrogen spectrum. So 3 to 2, there it is. Now that would be represented in quantum physics for babies as this. Whoa, here it is here. So the electron dropping down to a lower level and giving off the photon of light. So I think it's a bit much for babies, but anyway, grade 12s liked it. So that's the second interaction you could have. Another interaction could be, I'll get rid of this now. So there's 2 possible interactions you could describe. Now these aren't the 5 that the syllabus wants you to talk about. These are just you getting practice. Here's another one. It could be this. So, and what you'll notice, that's the photon. What you'll notice in each of these 3 so far is that we've got 3 lines at the vertex. We've got 2 leptons, so they have to be leptons or quarks, and the third line is a boson, a gauge boson. So 2 leptons and a gauge boson, 2 leptons and a gauge boson, 2 leptons, gauge boson. Here, what's happening here, 2 electrons are coming together, and that's probably not a good one. A better one would be, no, that won't happen. That's 2 electrons turning into, that wouldn't happen. Let's make it this. Electron and a positron. This could happen. Sorry about that. So electron and a positron coming together. So you could imagine, I haven't got these things, but you can imagine, here's my electron and here's my positron, which is a positive electron, coming in like that. So they're meeting and they annihilate each other and turn into a flash of light, if you like. Now, a lot of physicists will say, hang on, you'll always get 2 photons when that happens. But Feynman diagrams aren't representing the numbers of photons there. They're just representing a gauge boson of some type. Links what's happening on this side, the incoming interaction, with what happens later on, which will be an outgoing interaction. Okay, so they're the main parts of it. So that gives you a bit of an idea of how you can interpret it. Now I'm going to have a look at the 5 different types, and then we'll talk about how you state the interactions. Okay, now you have to know these off by heart. There's a QCAA has put out a little booklet on Feynman diagrams, and it has listed the 5, plus it's given some hints about some of the conventions. It's in the textbook. It'll be in all textbooks. It's fairly straightforward. Okay, the first one is the electron-electron interaction. Now, when electrons come together, this is what can happen. Can you imagine, here's one electron, here's another electron coming in. Now the arrows are both going in the same direction, and like I had before, these are, these are two electrons coming in. Now, so two negative particles approaching each other, if you like. Now when they get to there, you know that negative particles are going to repel each other. Look, let me just show you something that might be easier to appreciate. Imagine this is two, let's say you've got two magnets. Now this is nothing to do with magnets, so I'm using magnets as a bit of an analogy. Let's imagine you've got two magnets and the like poles are coming in. So you know that like poles repel, just like charges repel. So they're coming together. Now you know what's going to happen if you do that. They're going to push each other away. They're going to push away like that. The question is, what's pushing each other away? Now you could say, well, these electrons have got it's a negative charge on them, and the negative charges are pushing away. But how do negative charges interact? Okay, it's just like saying, how do two north poles interact? Well, what we say is that, look, I'll use this as this is my, if you like, a gauge boson. This will be my photon, what's called a virtual photon. But what's happening is, as they come together, they exchange a virtual photon. Now that exchange process moves them apart. Okay, so you don't have to understand how it works, just so long as you can appreciate that they exchange this particle. And that's why we call these gauge bosons exchange particles or mediating particles. Mediating means they're in the middle of the interaction or exchange. They're being exchanged by each of these electrons, or in this case magnets, because after all a magnet is just a moving electron. Really, it's an electric current in the ends of the magnet. So they're exchanging a gauge boson. Now we represent a gauge boson as a line like that. Okay, so we've got a vertex, and then they're going to move away. So this one will go up like that. This one will go down like that. Now that's diagram number one, electron interaction. You have to do that. The syllabus or the question on the multi-choice on the external exam could say, draw the Feynman diagram for an electron-electron interaction. Now you could do that. You could, what's another one? You could probably get away with just doing this part here. No, you could probably get away with that, you know. Now I wouldn't suggest you do it, but for instance you could say this is happening. An electron is giving off a photon and goes like that. Now that's still an interaction. You've got that, the photon, and that's this thing here I was telling you about, where the electron jumps to a lower level and gives off a photon. Now it's not one of the 5 diagrams, but I know in the external exam you'd be given your marks for that, because after all it's an electron-electron interaction. Excuse me. But I'm going to stick to the 5 main ones. So how do you describe that? The question is, describe the interaction. You'd say 2 electrons approach, as shown by those arrows. They exchange a virtual photon. So this thing here is, it's called a virtual photon. Now you'd probably get away by saying they'd exchange a photon. I'm not sure if you'd have to say virtual, but you know it's called virtual. Now virtual means it's not a photon. I shouldn't say it's not a real photon, but it's not the photons of light that you're familiar with. Now, things are coloured. That red is coloured because red light is coming towards your eyes. Now, if this was a regular photon from electromagnetic radiation, it would have a certain wavelength or frequency and colour and speed and all the rest of it, and no mass. But these things, virtual photons, they're just particles that satisfy the sort of mathematical calculations between the incoming. Now, the incoming will have a certain mass, it'll have a certain momentum because they're coming in at certain speeds, and they'll have what we call the spin. They'll have a certain spin, and then there'll be the outgoing. They have to, remember, you've got to conserve momentum, energy, charge, lepton number, baryon number. So the incoming lepton number is 1 and 1 is 2, and the outgoing is 1 and 1 is 2. The baryon number is 0 and 0, 0 and 0. So the conservation of charge, you've got 2 negatives, 2 negatives. The other thing you'd have to conserve is momentum and energy. So the momentum of that, the difference in momentum between that and that, has to be accounted for by something going on between, and this linking particle, and in this case it happens to be a virtual photon, so it doesn't have the normal photon properties, it's a virtual one. So description again: 2 electrons approach each other, they exchange a virtual photon, and then they scatter. Now, a good word for this is to scatter, because what they do is they're scattering away. They're coming in like this, and then they don't touch. Well, who knows what they do, but they exchange a virtual photon and then they move away. So it's like 2 billiard balls coming in and going like that, except they don't touch. They exchange this virtual photon. So from above it sort of looks like what happens on a billiard table, but you don't want to take the billiard table analogy too far, because the billiard table would have displacement versus time and so on, or displacement, distance, whatever. Okay, so that's the first one. The second one is this: electron positron. Now, I think the second one is the scattering. This is called scattering. Now you could just call it electron-positron scattering, or electron-positron interaction if you like, but it's more than an interaction because there's 2 types. Now, the guy who investigated this is BHABA, Bahaba scattering. Now, again, you don't have to know that name, but I'd call it electron-positron scattering. Okay, so what you've got is the electron coming in, and it meets a positron. So remember, positrons appear to go backwards in time. Wait a minute, this is scattering, sorry. So we have to do it like this. Now, they approach each other, but they exchange a virtual photon, and in the same way as before. So that's your photon, and they go off like this. Okay, so that's scattering, because the electron and positron come together, they exchange the virtual photon, and then they move away. Now, their properties might be different. They might have slightly different, this might have a different momentum to what it started with, and so on, but there'll be all the conservation laws would have to apply. And it's the photon that links the two. In some books they call it the coupling constant, because it's some device that physicists have dreamt up to explain that procedure. So that's electron-positron scattering. The other thing you can get is, if you're trying to explain that, you'd say an electron and positron approach each other, they exchange a virtual photon and scatter off, scatter off still has an electron and a positron. You could say in different directions, but you don't, it's not really talking about direction so much. Now this is annihilation, A-N-N-I, I think that's the spelling, annihilation. Okay, now that means basically to wipe each other out. So you've got this, so there's the electron, and here's the positron. So they're coming together, but instead of bouncing off, they actually combine, and when you think about it, their charges will cancel out. So this particle here, and remember you have to have a gauge boson as the third part around a vertex. So this is a gauge boson, and so it's a gamma particle, a gamma symbol, which is a photon. And then what happens is you get this. Now, so here's the annihilation part. So that's annihilation, I-H-I-L-A-T-I-O-N. So that's basically the two particles combining and turning into a photon, or several photons, but at least a photon. That's the gauge boson. And then the second part of the interaction is the gauge boson. Actually, this is called pair production. I'll just get a better pen. Pair production. Now, what's happening is the photon is now, if you like, decaying into a pair of leptons, in this case the electron and its antiparticle. Okay, so that's the pair production. So in this case you'd say electron and positron approach each other, they collide, or whatever you want to say, they interact and form a virtual photon, and the virtual photon then, and you don't know how long, this could be a billionth of a second, virtual photon then pair produces, if you like, another electron and positron. And that's it. That's all you'd have to explain. Okay? So that was the third one. Sorry, I should put a 3 there. That was the third of the 5. Now the last two are a little bit more complicated because they implicate. Now we'll just do this one, and then the last one is the same thing in a different sort of format. So this is neutron decay. Now I said to you before, if you're going to remember any reactions for this unit, just remember neutron decay, and you can explain a lot of your other concepts in terms of that, because you'll understand the particles involved, because you're going to learn that off by heart. And if you then can write it as a part of some answer, the examiner will look and say, well, you understand enough about neutron decay, you're trying to explain how it works or how other symmetry properties happen, and I'll talk about symmetry a little bit later. Okay, so what you've got here is a neutron. Now, a neutron will decay, and what it does is it decays into a proton. Okay, like that. Now, if you think about it, back in chapter about 5, I think it was, where we talked about natural radioactive. This is in Unit 1. You talked about natural decay, and you would have seen this. So it's in the textbook, but these are the things you get. And oh, it's not that. It's a neutrino. So it's that. But you know, if you remember back, this is basically a beta particle, a beta decay. So that's the beta decay of a neutron. Now that's grade, well, no, I shouldn't say grade 11, that was Unit 1 work. And and I would have stressed to my classes, and probably it's in the textbook, that there's always a neutrino associated with the emission of an electron. It's an anti-neutrino, so it's an electron anti-neutrino. So what you're trying to do is represent neutron decay with a Feynman diagram. So we've got that part done. Now we have to represent these things. Now if you remember back to when we did fundamental forces and the three different types of forces explained under the standard model, one of them was the weak force. And you might remember the weak nuclear force was explained by the decay of a W plus or a W minus particle. Okay, so in here we're going to have a W minus or W plus. Now, so we need a gauge boson. There it is there. You've got the three particles around the vertex. Two of them are, as I said before, fermions, in other words quarks or leptons, and this is a quark composite, and you're getting this. Now when you look at just that part, you'd think, well, if this is a positive particle, this thing must be a negative particle. And you know it's something to do, it can't be one of these two things because they're particles. It's got to be a gauge boson. Now you learnt that the gauge boson associated with the electrons and the weak nuclear forces was a W boson. So this has to be a W boson, but because that's positive, this has to be negative. So that's a W negative. Now if you wanted to, you could put an arrow on that, but I'm not going to. The syllabus doesn't, and we haven't in the textbook. Okay, now after, that's the ingoing, so you have that happening, that's the interaction, and then you've got the second part of the interaction, which is the gauge boson. Now you need two quarks or leptons. Okay, so let's put the two lines in like that. Okay, so we've got the three lines, the two for the quarks or leptons and one for the gauge boson, and you'll need this. Now we're trying to indicate it's that because it's an electron, it's not an antiparticle, so its arrow goes in the direction of time. This thing here must be the electron anti-neutrino. So it's going backwards in time. There's your symbol for the neutrino, and it's an anti-neutrino. Okay, so that's the one you have to learn off by heart, just that. I'd be keeping that in mind because you can use that over and over again in other parts of your work. So when you get into the test, as soon as you're allowed to write something down, you could write that down. If you're not going to write down, you know, the names of the quarks and leptons and so on, you want to remember that. So test yourself on that one and keep it in mind. Now you describe this, you have to put this into words. You'd get this, a question like this would say, explain this interaction. Okay, explain the interaction that occurs in neutron decay. 3 marks. Okay, that's 3 out of 50 for getting this thing right. Now, one is to have basically the overall diagram, you know, looking like this. Now, by rights, you should write time and space up here. Now, I haven't done that because that's just assumed. But if you try, and in the textbook, of course, we've got that for each one. So the first thing you'd have to do is get the space and time axes right, and then you'd have something on there representing at least the neutron and, you know, incoming. Now you might get bits of it mixed up, but at least you get 1 mark for getting the idea of the Feynman diagram right. The second mark would be, I'd say, for something like that. So there's 1 mark for the basic diagram, 1 mark for the neutron-proton part of the diagram, and then another mark I'd suggest for describing that. So this is what you'd say. A neutron decays into a proton and a W minus particle. Now you might say a W minus gauge boson. The gauge boson then decays, the W minus gauge boson then decays into an electron and an electron antineutrino. Right? So there's your second mark. Now basically you'd get your 3 marks for doing what I said there. Now there's 2 ways you can draw this. This is diagram 4. Now neutrons and protons aren't quarks, they're composites of quarks, and if you remember they're baryons. So this could be called the baryon picture of neutron decay. It's usually called, that particular one is the hadron depiction. Okay, because you're depicting the Feynman diagram or the particles at a hadron level, which is the neutrons and protons. You're not breaking them up into quarks. And you can see diagram 5 is the neutron decay using the quark depiction. Okay, so we better do that. I'm going to replace these by 3 quarks and that by 3 quarks, and then we're finished. Okay, so I'll get rid of all of this and let's have a look. Rid of that, and look, what I'll do is I'll write down the quarks here, so you might help you work this out. This is an up, down, down quark, and this is an up, up, down. Okay, so let's now do this. So here's your three quarks coming in. Now that's your neutron, if you like. Whoops. So that's a neutron, and you've got 3 quarks all together in the particle, in the nucleus, or in the confines of a neutron. Now what you'll notice is up and down, what you've got is one of these down quarks is turning into an up quark. So can you imagine that one there is turning into an up. So you've got a down turning into an up. So let's make this our down quark, and this we can be up and down. Okay, so the neutron is up, down, down, and one of the down quarks, let's say the bottom one, just to keep it neat, is going to turn into an up quark. So these quarks aren't going to do anything. They're just going to go up like that. And so there's your up, down. Now this one has to turn into an up quark. So this down is turning into an up quark. There it is there, the down turning into an up. So this is your proton. Okay, so you've gone from neutron to a proton merely by changing one of the down quarks into an up quark. Now that's going to happen. Now basically they're not doing anything. They're just spectators, if you like. I know things do happen. There's a change of, gluons are going back and forth and so on. But let's just keep this simple and pretend that they're just spectators. Just like in chemistry you'd have spectator ions and so on. They're there, but they're not interacting to form, well, they're not doing particle interactions. So this thing here, if you remember before, was a W minus. Now does that make sense? A down quark, if you think about it, is minus 1/3, and this is plus 2/3 of an electric charge. Okay, so this has to be basically 1/3. It has to be a negative. Wait a minute, 1/3. What have I got that plus there for? Minus 1/3 of an electric charge. Minus 1/3 E, yeah, that's right. So this has to be a minus, so that the sum total of the charges is equal and opposite to that thing there. So this accounts for the change in the electric charge. So W minus, now that then splits up into 2. Again, it's the E minus and the electron antineutrino. And again, it's going backwards in time. Now this one is your quark depiction, or quark notation is another way of saying it. Okay, quark depiction, quark notation, whatever you like. It's not a term you have to use in the syllabus. It just says neutron decay, 2 methods, and that'll be it. Okay, and so in this case you'd say a neutron made up of up, down, down quarks decays into a proton by one of the down quarks changing flavour. Remember, they're the flavours, the 6 up, down, charm, strange, top, bottom are the flavours, the 6 flavours of quarks. So we're having a flavour change here from a down to an up. So you'd say the neutron, which is made up of an up, down, down quark, or quarks, undergoes a flavour change for one of the down quarks into an up quark, and at the same time emitting a W minus gauge boson. So, and again you'd have time and space, so you get 1 mark for doing that, saying up to there. What's 1 mark for getting the basic diagram right, 1 mark for explaining what I just said about the flavour change, and then the final mark for saying the W minus gauge boson then undergoes decay into an electron and an electron antineutrino, and you're finished. Now that's all you'd have to do. That's all of them. Now in the textbook I threw in a couple of others. I did a proton. Now protons I don't think they've ever seen them decay. The decay time for a proton is at least, I think they believe, 10 to the 50 years. So a proton turning into a neutron, a half-life of, I think, 10 to the 50 years. So way beyond the age of the universe. So it's not something that happens. But I mean, in theory, or not in theory, but you could draw up a Feynman diagram to represent it, where you'd have the proton here, the neutron there, and guess what? What would you have instead of a W minus particle? You'd have the reverse of that, W plus, and you'd be getting positrons and electron neutrinos and so on. Okay, I'm going to finish there. That's all I think you have to do. I've talked to you about how you get your marks for that. So basically, learn the conventions I mentioned at the beginning, the 4 conventions, the couple of conventions about what happens in particle interactions. You know, use the vertex and the 3 particles, or the 3 lines at each one. And then if you want to explain any of that, you could use it in terms of electrons coming in with light, and electrons jumping to a higher level, and all that stuff I did. Then you'd move on to the 5 different types of Feynman diagrams that the syllabus asks you to do, and you'd be expected to explain the interaction that happens with neutron decay using a Feynman diagram, and it might even say at a quark level, or a quark notation, or showing the quarks or something, 3 marks. Or it could say show the interaction between, one possible interaction between 2 electrons, and you'd show the 2 electrons doing their scattering, and you'd explain it, and don't forget your axes. Or you could have a question could be describe or explain the possible interaction between an electron and a positron, and there's 2 there. You choose one, draw your diagrams, explain it in words like I did, use all the right terms, make sure you use gauge boson and words like exchange, exchange particles or mediating particles, gauge bosons, and describe the outgoing ones. You might even say the antiparticles are represented by arrow backwards in time. Get your full marks. Okay. Now really, in the whole external exam, I couldn't imagine you getting more than 1 multi-choice worth 1 mark on something to do with this, and 1 short answer question worth maybe 3 marks. That'd be the sum total of your Feynman diagrams, the questions on the external exam. So good luck with that. Thank you.